Hi, thank you for coming to see my talk today. My name is Mark Stevens, and today I will show you that even if your device gets old, it can still run just as fast as the newest thing out there. Before I start, I would like to thank my late grandmother, Clark Jones Lewis, for her complete support and love during the project. Unfortunately, she is unable to attend, but she has my never-ending love and thanks. I would also like to thank Mr. Dutton for his expertise with the required tests and the patience through the project. Without my parents, I would not be here to contribute this project to society, and for that I thank them. Finally, I would like to thank all of you for attending my talk. I appreciate your interest. Everyone here has a phone. I am sure a good bit of you play Candy Crush and Castle Crashers, and you've noticed that your hand gets warm from the phone. This concept is what my talk is about. Inside of everyone's phone is a central processing unit, or CPU. This is the brain of the device and takes the information received from the touchscreen and buttons and creates instructions for the rest of the device to execute. The same is true for desktops. For my experiment, I used an i5 6600K to test the change in temperature. Clock speed is how fast instructions are executed. A fixed number of clock cycles are needed to execute each instruction, which is why it is measured in gigahertz. The faster the speed, the more instructions can be executed per second. For example, the new iPhone 7 has an A10 CPU running at a maximum of 2.2 GHz, while a desktop i5 6600K runs at a maximum base clock of 3.5 GHz. There are other differences that affect performance, such as architecture and expansion buses, but as a general rule, the higher the clock speed, the faster the processor. As we all know, when we work out, we get hot and sweaty. This is because a byproduct of work we do is heat, and the way we cool ourselves is through perspiration. Just like us, CPUs heat up when they do work, and just like us, they need a method of cooling off. The traditional way of cooling CPUs is through fans. The metal heat sink sits on the CPU and takes heat away from the center and into the fins. The fan pushes air through the fins, cooling them and keeping the CPU cool. I used the stock fan found at the top and the Hyper 212 Evo found at the bottom to conduct my tests on air cooling. A new and popular way of cooling desktops and even some laptop CPUs is water cooling. The water block is usually made of copper and is placed directly on the CPU. Inside of the block are micro fins that help dissipate the heat by moving it from the center and into the fins. Water is pushed into the block and cools the fins and the CPU, and the warm water is brought out of the block and to the pump, where it is pushed into the radiator and cooled by fans before being pushed back into the CPU block. I used the ID Cooling FrostFlow 120L found at the top and the Corsair H100i found at the bottom to conduct my tests on cooling. Extreme cooling is an entirely different breed of cooling CPUs. Common methods include phase change systems and the use of liquid nitrogen. Phase change works by compressing a gas into a liquid and forcing that into a condenser and over the CPU, where it then evaporates and produces temperatures between -15 and -150 degrees Celsius. The gas is pushed back into the compressor and the cycle begins again. Liquid nitrogen works by placing a cauldron of sorts into the CPU and insulating the area surrounding it. The cauldron has holes milled into the bottom to maximize the surface area affected by the liquid nitrogen. Liquid nitrogen is poured in repeatedly as it evaporates, and overclocking is accomplished during that time. These extreme methods are expensive and dangerous to the components and even the person. Unfortunately, expenses ran too high and time ran out, so I was unable to test either. For the experiment, I used an i5 6600K desktop processor. It has a base clock of 3.5 GHz and turbo boosts up to 3.8 GHz. I placed the CPU into an open air test bench with top of the line parts to remove any outlying bottlenecks. I used Prime 95 to stress the CPU for 60 seconds and IDA 64 to record the temperature. Prime 95 is a software designed to find prime numbers and extremely CPU intensive. It is a popular tool used by overclockers to test stability. IDA 64 is a software that reads out detailed specifications of the computer. It has a tool used to monitor temperature. This temperature was compared to that of another software, HW Monitor, to ensure accurate temperature readings. I found the idle temperature and the maximum temperature reached during the stress test and subtracted the idle temperature from the maximum temperature to find the change in temperature. I conducted the Prime 95 stress test 20 times on each clock speed, which included 3.7, 3.9, 4.1, 4.3, and 4.5 GHz. I turned Turbo Boost off to prevent automatic overclocking and was unable to run the processor at the base clock of 3.5 GHz without the Turbo Boost on. In the experiment, two classes of cooling were used: air, represented by the stock cooler in the far left, and the Hyper 212 Evo in the middle left, and water, represented by the ID Cooling FrostFlow 120L in the middle right, and the Corsair H100i on the far right. In total, 400 tests were conducted, not including preliminary tests. My alternative hypothesis was that change in temperature would be greater in the stock cooler, less in the Hyper 212 Evo, less in the FrostFlow 120L, and least in the H100i. My null hypothesis was that the change in temperature would be the same in all tests. This graph shows average change in temperature between the different cooling apparatuses and clock speeds. On the x-axis are the clock speeds 3.7, 3.9, 4.1, 4.3, and 4.5. On the y-axis is change in temperature from 0 to 80 degrees Celsius. The legend shows the cooling apparatuses stock Hyper 212 Evo, FrostFlow 120L, and H100i. The error bars show the variation in the data. If you look at the stock data in the light blue, you will notice it has a slope of 0. This is because when I ran the Prime 95 stress test, the CPU reached the maximum temperature of 100 degrees Celsius and thermal throttle to prevent itself from going any higher in every test on the stock cooler. This graph shows average change in temperature between the different cooling apparatuses. In the x-axis is the cooling apparatuses stock Hyper 212 Evo, FrostFlow 120L, and H100i. On the y-axis is change in temperature from 0 to 80 degrees Celsius. The error bars show the variation in the data. I ran an analysis of covariance, or an ANCOVA, because it met the assumptions of linear relationships between independent and dependent variables. The linear relationships are parallel, and there is homogeneity of error variances. I ran the ANCOVA using the software R. After running the test, I found a p-value of 2.1 times 10 to the negative 16, which was a p-value being less than 0.05. I was able to reject my null hypothesis. This proved that there was a direct relationship between the cooling apparatus and the clock speed on the change in temperature of the CPU. Performance is increased by overclocking. Overclocking increases heat input. Heat damages to CPUs. When using a water cooling apparatus, there is less variation between idle and maximum temperatures. This allows for higher clock speeds to be held for a longer period of time. The Hyper 212 Evo retails for $30, while the H100i retails for $110. Cost is a major deterrent for consumers and prevents major technological improvements. On a more local scale, this can be applied to your personal desktop and laptop and even your phone. Providing adequate cooling can allow the device to perform better and extend the lifespan by removing the stress of excessive heat. Here is a custom water cooling setup that is cooling both the CPU and all 4 GPUs. While this is able to be done, it is much easier and safer to use an all-in-one kit that you can buy at Best Buy or any other local stores. You can water cool some laptops, such as this Asus ROG GX700, which has a special attachment that snaps to the back and pushes water through pipes built into the laptop. In 2015, Fujitsu developed a loop heat pipe to be used in phones. The conventional approach has been to install sheets of metal that has high thermal conductivity to transfer heat away from the CPU. With increased amounts of generated heat, however, this method is no longer sufficient in transferring heat. Fujitsu's solution was a loop heat pipe, where a fluid is inside of a flat tube that takes the heat from the CPU and is evaporated and relocated away from the CPU, where it cools and condenses. With this method being up to 5 times more effective at transferring heat versus the current method, it provides more room for performance enhancements. On a larger scale, you see a varied mix between massive warehouses with industrial fans blowing on servers, like in the picture on the top, of the fans that cool Facebook servers, and tanks of servers submerged in a non-conductive fluid, such as mineral oil, like the servers in the bottom picture found at the University of Leeds. Using the data I have found, even with the additional cost, water cooling allows for an improvement in cooling, and that allows for better performance longer down the road, allowing companies to avoid replacing parts longer and saving more money.